the crystal structure is something that in fact you have probably learnt off from high school days, and certainly maybe early college days you have heard of crystal structure, you have heard a lot of descriptions of it and so on. So in those descriptions you would have heard of crystal directions, in other words axis, and crystal planes. So there are conventions based on which we designate the directions and planes and so on, and on that basis you can have lot of the crystal structures that we have in the books. Okay, so these are there. Normally these are in dimensions of length. We basically certainly crystal axis, when we unit vectors we say with respect to, so we define unit vectors. Dimensions of length. Okay, so this is how it is done. We write x y z coordinate system, we say and if you take a real crystal structure you may have specific dimensions in the form of say of the order of say 2 angstroms. Interatomic spacing is of the order of 2 angstroms, say 1.5 angstroms, 1.8 angstroms. Angstroms is 10 power minus 10 meters. So it is still in the dimensions of length. Okay, so when you normally put such information together, okay, so we would call this as real space. Okay, real space is what we are conventionally used to, which where we write an xyz coordinate system, and within the framework of that xyz coordinate system we define dimensions, we define unit vectors, we define directions, we define the planes and spacing between planes and so on. So this is real space. Okay, what we are going to do today is define something that we will call reciprocal space. We will define something called reciprocal space, and we will begin to see some of its properties. Okay, reciprocal space in fact takes the basic approach here is that the same crystal structure information that you have here and many of its important key features can be represented in another format known as reciprocal space. Okay, so we are not actually changing anything in a fundamental sense, because you are still talking of the same material, you are still talking of the same I mean relationships between the planes between those materials, the atoms between those present within the materials and so on. So we are not fundamentally changing anything. All we are doing is we are representing the same information using a different set of a different framework, if you want to call it that. It is a different framework which is called reciprocal space. Here the dimensions of the vectors we will use will be 1 by length. Okay, so dimensions used will be 1 by length. Or length power minus 1 is the dimension that we will use. In sort of a trivial sense you can see that this can be related to our k vector, because k vector is already in the dimension of 1 by length. Okay, so therefore it may make it easier for us to relate certain things associated with the wave vectors of electrons which are running across the crystal structure to the crystal structure itself. Okay, if you use the same framework within which you are describing both of them. The framework here we are using is 1 by length, 1 by lambda. So it would help if we also defined the crystal structure in 1 by length dimensions. Okay, so that is maybe a little bit of a trivial way of saying it, but it certainly conveys the immediate link between what we have just done up until now and what we are planning to do. Okay, in reality actually it is much more than that. It turns out that many of the information you can represent in 1 by length in this reciprocal space actually conveys certain details of how interactions occur between a crystal structure and waves that are present much more elegantly than is done in real space. Okay, so in a broader sense this conveys certain information much more elegantly, reciprocal space. and actually is able to highlight specific details much better than the real space way of representing information does. And that is the real that is the fundamental reason why actually if you get into diffraction, if you get into diffraction as a means, as a tools of as a tool for looking at structure and such information, characterization of materials, you will find a lot of heavy usage of reciprocal space. The first time you encounter reciprocal space, it is not as intuitive, and it may seem like we are unnecessarily complicating the issue, so to speak. Okay, so it look like why go to all the troubles of creating everything in 1 by length when real space is already there for us. It is just that if you use it enough, you find that there is a lot of information that is much more elegantly and clearly represented in when you use this notation than when you use real space notation. So it is from that perspective that this has really caught on, and it traces itself back to a person by name Ewald, who actually worked on this in around the year 1920. Okay, so around that time frame was when this work was put together, and so there is notation which is named after him also in this relationship. Okay, so in this context. So we will see that as I mentioned, we have sort of indicated why we may need to go in for 1 by length dimensions, but that is not a hard and fast, that is not the best way of indicating it, but you can see the link that we have already got 2 pi by lambda for k wave vector, and we want to see the interaction between the electron waves and the crystal structure, and therefore it would help if we presented all the information in the same framework. So you can think of that as a loose link for why we are doing what we are doing. As we progress forward, we will see much more a better understanding of how this system works out. Okay, so now we will look at in the next 2 or 3 classes we will actually focus exclusively on reciprocal space, and we will build its relationship to the real space, because that is something we need to understand, and to some degree this discussion may seem a little disconnected from what it is that we have discussed so far. But we will need to build this framework so that we can connect it up, link it up to our discussion earlier, and see what benefits we can gain from the process. Okay, so but temporarily for at least this class and most of next class, this will be a discussion exclusively on reciprocal lattice and on how diffraction can as a phenomenon can occur in the reciprocal lattice. After that only we will make a link back to real lattice, real space, and also extend this idea that diffraction occurs in reciprocal space and it has a certain way of being conveyed, and see what is the consequence of that discussion on how the electrons are interacting with the crystal lattice. Okay, so that step is going to be at least 2 classes away before we get there, but now we will have to build the framework which will enable us to handle that discussion. Okay, so that is what we will do at this point. So when you look at real lattice, real space, we say that we are usually defining it by unit vectors, and typically we would use the notation A1, A2 and A3. Okay, so A1, A2 and A3 are unit vectors in real space. So we have a crystal structure in real space represented by these unit vectors A1, A2 and A3. Okay, now we will define a reciprocal space in other words we will define a space, we will define a coordinate system. So we are just going to define it upfront. This definition is at this stage may look somewhat arbitrary, we will just accept it as an arbitrary definition. The definition, the way it is given, will give the space a lot of useful properties which we can use later on. How arbitrary or otherwise this definition is, we will see a little later, but at the moment it is just a definition, we will just accept the definition and we will work with it. So we are defining it. Okay, so this is a choice we are making, so we are defining it, we are defining a reciprocal space to consist of 3 vectors, again unit vectors there, B1, B2 and B3, but these are not arbitrary vectors, they are being defined with respect to real space vectors in a certain way. In other words, there is in the process of this definition we are already making a link between these vectors and these vectors, okay. And what is that link? It is written like this. So B1 is A2 cross A3 by V. What this V is we will see in just a moment. It is a volume, actually volume of this unit cell of consisting of A1, A2 and A3. B2 is defined as A3 cross A1 by V, and B3 is similarly is A1 cross A2 by V. So these are cross product, these are vector cross products, so that is what they are. So so these are all vector quantities. B1, B2 and B3 are vector quantities, so they have magnitude as well as a direction. A1, A2, A3 are also vector quantities, they all also have magnitude and direction, and this is a cross product, and so it is defined that way. B1 is defined as A2 cross A3 by V, B2 is defined as A3 cross A1 by V, and B3 is defined as A1 cross A2 by V, okay. So this is the way they are defined. By defining it like this, certain properties become certain properties arrive for I mean end up being available for B1, B2 and B3, which becomes convenient for our utilization later on, okay. So now we will see what immediately based on this definition itself, simply because we have defined it like this, what is the meaning of what is the consequence or what is the relationship between B1 and these reciprocal. So these are called reciprocal lattice vectors, okay. These are unit vectors in reciprocal space, they are also called reciprocal lattice vectors. These are real lattice vectors and this is real space. So by simply using this definition, what is it that we have created as a relationship between what is the consequence in the relationship between B1, B2 and B3 with respect to what we have in real space. So that is the first thing that we will examine, okay. So to do that, let us take an arbitrary, say a triclinic cell, a triclinic cell is one where by definition the A1, A2 and A3 vectors need not have the same length. So A1 need not be equal to A2, need not be equal to A3, and the angles between them, so alpha, beta and gamma, which are the three angles that exist in the system, need not be the same, okay. So that is the, so in that sense it's like a very general cell, we are really placing no restrictions on it. Now we are defining, we will write B3 again here. Fine, A1 cross A2 by V. So now by definition, see volume does not have any, is not a vector, volume is just volume, it is not a vector, it is a scalar quantity. So you have A1 cross A2, by definition of cross product, if you have a cross product, the result is perpendicular to both A1 and A2, okay. So that is the meaning of a cross product. So B3 therefore by definition is perpendicular to A1 and A2. So on this scale, if you want to draw B3, it would show up something like this, it will show up somewhere in this direction, it would be perpendicular to the plane being described by A1 and A2, okay. So the planes A1 and, I mean the vectors A1 and A2 define a plane which we are now treating as the horizontal plane on this board, sort of in this representation, and B3 would now appear in this direction perpendicular to A1 and A2. So that is the definition, by way of definition. But what about its actual magnitude? If you look at A1 cross A2, if you see the by the standard definition of A1 cross A2, that is the area of this parallelogram, okay. So if you write this as the origin, you write this as OA, let us say this is B and let us say this is C. So the area of this parallelogram OACB is what is being given by A1 cross A2, okay. So OACB, area of parallel A1 cross A2, okay, OACB, the parallelogram. So that is what this area is. if you look at the volume of the unit cell, this V here is the volume of the unit cell in real space, okay. So that is the volume, that is that V. So which is that volume? If you take this A3 vector and you complete this solid, okay, so that solid, so this unit cell that we have drawn here, I mean if you draw it properly you will get it appropriately. This volume of this unit cell is this volume V that we have written here, fine. So that is the volume that we are looking at. So what is that volume in terms of geometrical terms? It is simply the area of this base times the distance between these planes or the height of this unit cell, okay. So that is all the volume is. The volume is the area of the base times the height of that structure. So that is what we are looking at. So the height is simply this the whatever, this is A, B, C, so this is D, let us call this D, OD. So OD is the height of this unit cell that we have drawn, and it is simply the projection of A3 on this axis which is perpendicular to A1 and A2, right. So that is the height. So we will call that so the height is OD, okay. So the height is OD. So therefore volume is the area of OACB into the height OD, okay. So it is the product of the area times the height, that is the volume, okay. So therefore if you look at it that way, B3, okay, or the modulus of B3 is area OACB by area OACB into OD. So that is what the modulus of B3 is. So these two will cancel out, so it is simply 1 by OD. So it is simply 1 by OD, okay. So that is the magnitude of B3. So B3 is in this direction and the magnitude of B3 is simply 1 by OD. What is 1 by OD? If you look at the conventional planes that we are looking at, if you look at the way we define planes, this is the 1 0 0 plane, okay. So if you look at 1 0 0 plane, this is the D1 0 0 plane, it is the spacing between 1 0 0 planes. If you go back to your elementary crystallography, the 1 0 0 planes are defined this way, and then these or the 0 0 1 planes, D 0 0 1, this is perpendicular to A3 axis, okay. So D 0 0 1, if you want to call it 0 0 1, it is the spacing between 0 0 1 planes. So spacing between 0 0 1 planes is what we have now looked at. So OD is the spacing between 0 0 1 planes, so D 0 0 1 okay. So B3 is therefore spacing this is the standard notation for crystallography. So if you go and look up crystallography from your elementary crystallography, this is D001 is the spacing between 001 planes, and modulus of B3 is simply 1 by D001, okay. So therefore we find, and by analogy, in fact if you extend this argument, the same thing would hold for the other ones too. B1 is 1 by D100, B2 is 1 by D010, and B3 which we just did is 1 by D001. So B1, B2 and B3 are inversely proportional to the spacing of those planes 100, 010 and 001 planes. So that is the by way of our definition we have created the situation, okay. So it is not, it did not arbitrarily occur, since we defined it this way, this is the way it has occurred, okay. Also if you look at the way we have defined it, we will also see that if you just take a product say B3 cross A2 or B3 dot A2, okay. If you just take this dot product between B3 and A2, I have just arbitrarily picked these two vectors, we find that since B3 is already perpendicular to A1 and A2, this dot product is 0, okay. So by definition it will be, there will be a cos 90 degrees which shows up here, therefore this is 0. Similarly B3 dot A3 sorry A1 equals 0, because B3 is perpendicular to both A2 and A1 simply based on how we have defined it, that is all it is, okay. So therefore these two are 0. If you look at B3 dot A3, okay, based on our definition, if you go back to our the picture we have drawn here, B3 has the is this distance OD, I am sorry, this is 1 by the distance OD, so which we just saw here, okay, 1 by OD, B3 is modulus of B3 is 1 by OD, so this is simply equal to 1 by OD times the projection of A3 on B3, okay. When you do a dot product, that is basically what it is one vector times the projection of the other vector on itself, okay. So what is the projection of A3 on B3? Projection of A3 on B3 is OD, A3 on B3 the projection of A3 on B3 is OD as shown in this diagram, fine. So therefore the dot A3 that we are having in that dot product is simply works out to OD, so to speak. So this projection will become OD, okay. So therefore this is equal to 1. So we find the relationships between those vectors, the reciprocal lattice vectors and the real lattice vectors based on how we have defined those vectors, okay. Based on how we have defined those vectors creates the situation where B3 dot A2 is 0, B3 dot A1 is 0 and B3 dot A3 is 1. So more generally, if you have Bi dot Aj, then this is equal to 0 when I not equal to j and is equal to 1 when I equal to j, okay. So that is the notation that we have, and that is the consequence of what the way in which we have defined these vectors, okay. Now we have already seen, if we have taken a specific case actually where we are saying that if you have a particular vector, so d b1 in this case is a particular vector, and we found that the way we have defined it, it works out to be perpendicular to the two vectors A2 and A3, and it is equal, in magnitude it is equal to 1 by the spacing d100, okay. In reciprocal lattice we can actually generalize this much more. We will generalize it as follows: we can write any vector h hk, h is the notation that is given for a reciprocal, a generic reciprocal lattice vector, okay. So where we it could be anything, so h is a general reciprocal lattice vector, we will give it subscripts hkl, okay. So if this is a reciprocal lattice vector and the unit vectors in the reciprocal space are b1, b2 and b3, then this is simply equal to h b1 plus k b2 plus l b3. This is simply based on our definition and vectorial, standard vectorial notation. Standard vectorial notation, b1, b2, b3 are unit vectors, and h, k and l are the specific distances we are travelling along those unit vector directions, okay. So h, h, k, l is a vector in reciprocal space, and it is therefore equal to h b1 plus k b2 plus l b3. Those h, k, l are the amounts that we are travelling on those respective directions, okay. So that is what it is. We say that when we define, when reciprocal space is defined the way we have just defined it, then when you take a general vector h, h, k, l, okay, in the reciprocal space, we can, there are some relationships it has to real space vectors and dimensions in real space, just the way b1, b2, b3 themselves have relationships to the a1, a2 and a3, okay. We just saw relationship between b1, b2, b3 and a1, a2, a3. Similarly, there is a very general relationship between any HKL vector in reciprocal space and certain quantities in real space. What is that relationship? it is basically that HHKL is perpendicular to the plane which has the Miller indices HKL and modulus of HHKL is equal to 1 by DHKL. Please note, in both these cases we are relating something in reciprocal space to something in real space. This is not complicated because we just did that already when we looked at A1, A2, A3 and B1, B2, B3, and we made relationships between them when I said that B1 is 1 by D 100, B2 is 1 by D 010 and B3 is 1 by D 001. There B3 is a reciprocal lattice quantity and D001 is a real lattice quantity. We found that simply because of the way we have defined it, when in our definition itself we have linked real space and reciprocal space. So they are not arbitrary quantities, okay. So they are already linked by definition, therefore some quantity in real space can relate to something in reciprocal space within the framework of that definition. So that is basically all we are doing here. This is a reciprocal lattice vector and it is found that it is perpendicular to a plane in the real lattice which has the Miller indices H, K and L, and the modulus of this reciprocal lattice vector is 1 by D H K L. These are properties that the reciprocal or in other words 1 by the spacing of HKL planes. So these are two properties that any vector in the reciprocal space has as a result of the definition of the reciprocal lattice, okay. So right now I have just stated it. In the next few minutes we will prove these two. Once we prove these two, we have a good understanding of what holds in reciprocal space and how it relates to real space, and later we can use those two, okay. So we will now try attempt to prove this. So to do that, let us actually draw a general plane in the real space. So we will say that we have so this is A1, this is A2, this is A3, okay. So these are unit vectors in real space and we will draw the HKL plane here, okay. So this is HKL plane, fine. So now we will just say that in reciprocal space we have the HKL. We at this moment I am just arbitrarily denoting it here. This is an arbitrary denotion at the I have arbitrarily denoted it this way. I have indicated it here in this figure this way, simply for sake of convenience to show it in the same figure. What relationship it actually has to HKL is not forced upon it simply because of how I have drawn it. We will show that in fact it does have some appropriate relationship. So that relationship we will just see, we are actually going to prove it. Now by definition of HKL plane, its intercepts along A1, A2 and A3 are simply A1 by H, A2 by K and A3 by L. So these are the intercepts, okay, only because the plane HKL happens to intercept A1, A2 and A3 at those locations such that its intercepts are at A1 by H, A2 by K and A3 by L. That is the reason why we even call it the HKL plane, okay. So therefore if you see if you take this vector here, this vector here is A1 by H, this is A1 by H is this vector, that is why you get this H notation in the HKL plane, okay. Similarly this vector here will be A2 by K, that is why you will get the K notation. This vector here from here to here is A3 by L, that is why you get that L in the HKL, okay. So this is A1 by H. I will also name this locations where this plane intercepts A1, A2 and A3 as A, B and C, okay. So so OA is A1 by H, and OB, so this is the origin O, okay, OA, OB and OC. So OA is A1 by H, OB is A2 by K, fine. So this is what we have. So simply by vectorial notation, if you write OA plus AB, you should get OB, right. So OA, simply because of standard vectorial notation, OA, so these are vectors by the way, OA plus AB should equal OB. That is easy to see. If you go from here to here and then you go from here to here, it is the same as going from here to here, that is all it is. OA plus AB is OB. So this is what we have. Okay. So now that we know these are the vectors, we can replace them. OA is A1 by H and OB is A2 by K. So therefore A1 by H plus AB, vector AB should equal A2 by K, fine. So this is what we have. We can rearrange this a little bit. So we wrote A1 by H plus AB equals A2 by K. Rearranging this, we get AB is A2 by K plus minus A1 by H. So we now have in terms of the A1 A2 vectors, we have the vector AB given to us in terms of the unit vectors A1 and A2, which we have already defined for a real space. We already said that if you take a vector HKL, we are defining it based on this notation as HB1 plus KB2 plus LB3. So the H, K and L are simply integers, okay. So this is some vector in reciprocal space. So H, K and L are just integers. So as long as they are just integers, you can use them in whichever space you wish, they are just integers. B1, B2 and B3 are reciprocal lattice vectors. Therefore HB1 plus KB2 plus LB3 is now a reciprocal lattice vector, whereas when you use the H, K and L, which are just integers in the real space, A2 by K and A1 by H, if you take this difference which is AB, it is a real lattice vector, because these are just integers which you are using in the real space, okay. But they are the same integers at this time. We have the same H, K and L being used in two different places. The HKL plane is this results in this relationship, and the same HKL values we have now used for this definition, although we have got no significance for it yet, they are just same, we are enforcing the same HKL in this definition for HKL. So if you now take a dot product of HKL and AB, what will you get? So if you do HKL dot AB, okay. So we have B1 here, HB1, okay. We already saw that if you have AI dot Bj, then this is equal to 0 if I is not equal to j, and this is equal to 1 if I is equal to j, fine. And since it is a dot product, you can have it AI dot Bj is the same as Bj dot AI. The order in which you do this dot product is not important to us, because either way you will get the same thing. So if you look at this dot product here, you have HB1, HB1 dot A2, so these are just the H is just an integer, B1 dot A2 is 0 because it is 1 and 2 here, so that is 0, B1 dot A1 is 1, and you have a HB1 here and A1 by H here, so H and H will cancel, you get minus 1, okay. So HB1 times or dot product of HB1 and A1 by H will give us minus 1, fine. If you take B2 here, KB2 times A2 by K, the K and K will cancel, you will have B2 dot product of B2 and A2 which is 1 plus 1, and this B2 dot A1 is going to be 0 because it is a subscript 2 and that is a subscript 1, we already saw that by definition, so that is a plus 0, so that term will become 0. And then B3 dot A2 is going to be 0, B3 dot A1 is going to be 0, so this term does not contribute in any way, it becomes all 0, So this becomes 0. So this becomes 0, the product with this gives us a plus 1, the dot product with this gives us a minus 1. So this is equal to 0. So we have a situation where a vector in reciprocal space HHKL dot a vector in real space is equal to 0. So in other words, we have a dot product between two vectors which is 0, which simply implies that HHKL is perpendicular to this vector AB. Therefore HHKL is perpendicular okay. So if you go back to our figure, it means that this HHKL is perpendicular to this AB okay. So this AB is there, the way this HHKL is defined, it is perpendicular to AB. Using exactly the same derivation that we have done, instead of we started with this location being A1 by H and this being A2 by K, we can do the same thing with A2 by K and A3 by L okay, in which case we will find that HHKL will become perpendicular to BC. Similarly, we can also do it with A3 by L and A1 by H, and exactly the same calculations we will do, we will find that HHKL is perpendicular to AC. So we find that HHKL is perpendicular to AB, it is perpendicular to BC, and it is perpendicular to CA based on the same derivation that we have done. You simply have to select the other two axes, you will come to the exact same conclusion. The same mathematics will work out in exactly the same way. We will find that HHKL is perpendicular, the vector HHKL is perpendicular to the vectors AB, BC and CA. Therefore, and since all of these three are forming a plane, if it is perpendicular to any two, in fact even if it is perpendicular to just two, it is certainly perpendicular to two and it is also perpendicular to all three. If it is perpendicular to them, it is therefore perpendicular to the plane defined by A, B and C okay. Therefore HHKL is perpendicular to plane defined by ABC, AB, BC and CA, and therefore which is basically the HKL plane okay. So that is how those vectors are even defined. AB and BC and CA were defined based on the intercept at 1 by H, 1 by K and 1 by L in those respective axes. So therefore HHKL is perpendicular to HKL. So any so again we are relating something in reciprocal space, a vector in reciprocal space to a plane in real space okay, and again all these relations are coming about simply because our original definitions related a reciprocal lattice vector to real lattice vectors. So that relationship was already there. Within the framework of this relationship we are finding other relationships that hold. So we find that any HHKL plane which is therefore defined as HB1 plus KB2 plus LB3, where B1, B2 and B3 are the unit vectors in reciprocal lattice reciprocal space. Those HHKL vectors will automatically be perpendicular to the HKL planes in the real space okay. So this is already we have seen this, so we have just shown this okay. So the other thing we would like to see is what is the value of modulus of HHKL and how does this relate to the spacing of between the HKL planes. We will in fact see that this is equal to 1 by d HKL okay. So this is what we are just about to we are going to look at. We will come back to this figure. Let us say that a unit vector along HHKL okay. So we will let us first define a unit vector along HHKL, that is simply HHKL by modulus of HKL of HHKL right, that is the definition of a unit vector along HHKL. We will just call this say n cap okay. Now when you say a HKL plane is defined the way we have just drawn it okay, so when we say this we mean that that there is a similar plane like it at the origin then there is one at this location, then there is one similarly spaced next to it, similarly spaced next to it, and so on. That is the way we define a family of a set of planes. When you say a HKL plane, it is not just a single plane, I mean it is that set of planes that are parallelly there, we take the one closest to the origin and then take the intercepts of it, and that is how we come up with HKL. So there are planes correspondingly around. So therefore the spacing between the HKL planes is simply the distance between the origin and this HKL plane, right. The closest distance or rather the perpendicular the spacing between this origin and that location, which would then be the closest distance between this plane and the origin, is therefore the DHKL, right. So now we have basically seen that at that point the line drawn from the origin which goes closest to this plane will then go perpendicular to that plane, alright. So that is how you will get the location. So therefore if you look at the distance between the plane and the origin, we basically see that we can write that by saying HHKL or n cap dot A1 by H, okay. If you take the dot product of A1 by H and you take its what shall I say the dot product of OA with this vector in the direction of this HKL, then you get the component of OA along that direction, and that would then be the spacing that you are interested in, okay. So this is what you will get. So this is simply A1 by H dot product with you will have HB1 plus KB2 plus LB3 divided by the modulus of HHKL, okay. So this is DHKL, right. So DHKL is now defined this way, D between those planes is such that if you take the component of any of those intercepts along the perpendicular to that plane, okay. So that perpendicular is now going through that origin, so that perpendicular vector that is there, if you take the component of this vector along the direction of that perpendicular, you therefore get the distance in this direction, okay. So that vector, unit vector, is simply giving us the direction there, but if you take the component of this intercept OA along that direction, or any of those OB along that direction or OC along that direction, if you take the component along that direction, that would then represent that spacing between the origin and that point, which is then the closest spacing between the origin and that point, and that would therefore and at that point that vector will be perpendicular to that plane, which is what how we have defined it, okay. So if you take the component of the intercept along the perpendicular, that is the closest approach that the plane makes to the origin, and that is therefore the D spacing of that plane, because the next plane is sitting at the origin. So the DHKL is the component of this vector A1 by H along this unit vector here. The unit vector is simply defined by this, and this and since it is a dot product, we can interchange the it does not matter in which order we do it, so we will get this. So now if we carry out this dot product, what do we see? Again you have a A1 here, you have a B1, B2 and B3 here, and clearly A1 dot B2 is 0 and A1 dot B3 is 0, the way we have already seen. So only A1 dot B1 is going to count for anything else. So okay, so A1 dot B1 is going to be 1 because of the way it is defined, and the H and H are going to cancel. Therefore DHKL is equal to A1, so we will just write it here, A1 by H dot HB1 B1 or sorry A1 dot H by HB1 dot HB1 divided by modulus of HHKL. So this and this will cancel, A1 dot B1 equals 1, therefore this is equal to 1 by HHKL. So we see which is the proof that we set out to prove. So we see that HHKL is perpendicular to and modulus of HHKL is equal to 1 by DHKL. Okay. So what we have seen is we started off this class by saying that we need a notation which is this reciprocal lattice notation, because it will help us understand the interaction between the wave vectors corresponding to the electrons and the crystal structure, which basically conveys to us the periodic structure that is present between all the components that are present, all the atomic components that are present within the lattice, so to speak, the material that we have. So in that context we found indicated that that basically we might need to develop something in this reciprocal lattice notation, and it is that notation that will help us capture this interaction between the wave vectors and the periodic crystal structure. So in that context we defined reciprocal lattice to be consisting of B1, B2 and B3 with specific relationships to the real lattice vectors A1, A2 and A3. On the strength of that relationship, we found that on the strength of the definition, we found that already B1, B2 and B3 had specific relations to A1, A2 and A3, which then translated to a general reciprocal lattice vector HHKL having specific relationships to the plane HKL in real space. The relationships are that the vector HHKL is perpendicular to the plane HKL, reciprocal lattice vector perpendicular to a plane in real lattice, and the modulus of the reciprocal lattice vector is 1 by the spacing between those HKL planes. Okay, so this is the framework of our reciprocal space. We have already seen some important relationships here. In the next class we will see how diffraction, which is the interaction of waves with the periodic crystal structure, how that diffraction phenomenon can be represented in the reciprocal lattice notation.